Okay, so we're going to take a look at an example that we have actually used before, and we're going to apply what we call a floating line situation to this so that we can get into the excellence. The excellence is about changing parameters, so we're going to end up changing the parameter, but right now we've got 1, 2, 3, 4 feasible regions, and or 4 inequalities or constraints, and I'm going to shade them and draw them, and I'm going to shade them out. So I'm on Desmos and I'm shading them out. So we're going to end up shading them out and getting a feasible region that you should actually recognize, because this is a feasible region we've dealt with before. And we get these points as our key points, but we have 4 vertices, obviously. And this thing, this 3x plus y is equal to the profit, is our objective function. This is how we optimize or maximize or minimize what we're trying to find. Now, the next thing that we're going to do is something that we've never done, and this is the new bit. We're actually going to take the objective function and we're going to turn it into a graphable line. All right, we're going to actually graph that objective function. Now let's talk about how we do that, or why we do that, or how that happens. So if we've got this 3x plus y is equal to p, we can graph that. And let's just say if we make p 0, let's just make the profit 0. So here's the graph. It's going through 0, 0 initially. So let's rearrange this and make it y is equal to, and it's going to end up being negative x plus p, and we're just going to make p 0. No profit, 0 profit. So y-intercept's at 0. And this is our gradient. And we know that if we go from the y-intercept, which is at 0, 0, and if we go down 1, 2, 3, and over 1, we basically get a graph, a straight line graph. And so we can actually take this objective function now and turn it into a straight line graph and actually put it as a graph onto our feasible region area. So, I mean, with the nice thing about Desmos is that we can physically use a slider, so we can change p to be kind of anything, 2, 3, 4, and keep sliding it in this direction through the feasible region. Now remember, we're going to try to find the maximum profit. So we're basically, imagine you're sticking these points in. We know that if we stick them into the objective function, they both give us the same value. They give us 15. When we make the profit 15, the line is now right, those 2 points are now right on that line. It's parallel to that last line on the feasible region. And both those points give me 15. So that's that floating line thing, and it's lovely when you can do it with technology that actually makes you are able to float the line. And why is that important? That's important because it helps us if we want to change the constraint. So let's just take this 3x plus y is greater than 15. Let's change it. Let's change it so that we don't have that line anymore. We actually have changed the constraint to 4x plus y. Now our feasible region has changed. Now we have 2 new points, 2.25 and 6 and 3.75 and 0. Now how does this going to affect how somebody maximizes their profit? So what we do is we go back to our objective function, and nothing's changed with the objective function, so we just keep sliding that line, sliding that line, sliding that line, and look what happens. It goes through the 3.75 and 0 first, but hasn't quite reached the 2.256, and then now it has. Now it's like at 2 and 7, which is actually probably not that point, but I can't get the technology to actually hit that. So here we're saying the profit is about 13, and we'll have to check it. But that appears to be where we'll get the maximum P at that point, as opposed to getting the exact same profit as we did initially. So again, this was our initial thing, and when we slid out, we could get 15, and we can get 15 from both those points, 3 and 6 and 5 and 0. When we change the constraint, now as we slide out, we no longer get the maximum value at 3.7 and 0. We have new points. We're actually going to get less of a profit of around 13 as it last exits out that feasible region.